On March 11, 2011, a single valve in Japan's Fukushima Daiichi nuclear plant failed to reopen. That one mechanical hiccup helped trigger 3 reactor meltdowns, hydrogen explosions that blew the roofs off containment buildings, and a cleanup bill that's still climbing toward $200 billion more than a decade later. And you're about to learn the real reason why. The Fukushima Daiichi plant sat on Japan's northeastern coast, a cluster of 6 boiling water reactors built in the 1970s. Unit 1 was the oldest, and it had a quirky backup cooling system called the isolation condenser. Think of it as a passive heat exchanger. When the reactor scrammed and shut down, steam from the core would rise into external tanks filled with cold water, condense back into liquid, and flow back down by gravity. No pumps required, just valves, DC battery power to control them, and physics doing the heavy lifting. It was elegant, it was simple, and under the right conditions, it worked like a dream, baby. But there's a catch. Those valves were designed to close automatically during certain emergencies to prevent leaks. After the earthquake hit at 2:46 p.m., the reactors all scrammed successfully. Control rods dropped in, fission stopped, and everything looked manageable. But decay heat doesn't stop. Even with the chain reaction shutdown, the fuel keeps generating heat for days. Operators knew they had to manage cooldown rates carefully, so between 3:10 p.m. and 3:34 p.m., they manually cycled the isolation condenser valves 3 times, opening and closing them to keep the reactor temperature from dropping too fast. They wanted to stay under 55 degrees Celsius per hour. Standard procedure, textbook response. Then the tsunami arrived at 3:37 p.m., waves up to 15 meters tall, almost 3 times higher than the plant's 5.5 meter seawall. The water smashed into the basements, flooded the diesel backup generators, and drowned the electrical switchgear. Station blackout. All AC power is gone. Most of the DC battery systems failed within minutes. And here's where the valve becomes the villain. The isolation condenser valves in Unit 1 were fail-closed by design. When DC power vanished, they locked shut. Operators had no remote way to reopen them. The reactor was blind, instrumentation dark, and the one backup system that didn't need pumps was now sealed off by a piece of metal the size of a dinner plate. By 6:18 p.m., some DC power was partially restored. Operators tried to reactivate the isolation condenser by opening valves MO3A and MO2A. They saw steam briefly, a hopeful sign that cooling had resumed, but 7 minutes later at 6:25 p.m., MO3A was found closed again. The reason remains unclear. Some reports suggest operators misread indicators in the chaos, others point to procedural caution, operators worried that opening the valve during a blackout might cause uncontrolled leaks. Either way, the valve stayed shut, cooling stopped, and the reactor core began its slow march toward meltdown. Let's talk numbers. By 5:46 p.m. on March 12th, roughly 27 hours after the tsunami, water levels in Unit 1 had dropped low enough to expose the top of the fuel. At 6:46 p.m., core damage was confirmed. Temperatures inside were climbing past 2,800 degrees Celsius. Zirconium fuel cladding was reacting with steam, producing hydrogen gas. At 3:36 p.m. on March 12th, that hydrogen found oxygen and exploded, blowing the roof off the Unit 1 reactor building. The mushroom cloud was visible for miles. Radioactive material started leaking into the air and ocean, and all of it traces back, at least in part, to those few hours when the isolation condenser sat idle because one valve refused to open. Here's the thing, the isolation condenser's secondary loop, the cold water side that actually absorbed the heat, was still at 65% capacity when engineers inspected it later. If the valves had stayed open, if DC power hadn't failed, if operators had understood the system's state in the dark, Unit 1 might have stayed cool long enough for other measures to kick in. Units 5 and 6, farther from the flooding, had one surviving air-cooled generator and avoided meltdown entirely. Unit 1 missed that margin by inches and hours. One valve's closure stretched those hours into a tipping point. Units 2 and 3 faced their own nightmares. They relied on different systems, the reactor core, isolation cooling, and high pressure. Coolant injection setups, both of which ran on steam turbines. Those worked for a while. Unit 2's RCIC kept running for more than 3 days before steam pressure dropped too low. Unit 3's systems failed within 20 to 68 hours. Without AC power to recharge batteries or run pumps, operators had no way to inject fresh water once those steam-driven backups quit. Safety relief valves were used to vent pressure and try alternative injection methods, but delays in venting, caused by radiation levels and equipment failures, led to more hydrogen buildup. Unit 3 exploded on March 14th. Unit 2's containment breached on March 15th, releasing the highest radiation levels of the crisis. Unit 4, which was offline for maintenance, still exploded on March 15th because hydrogen migrated through shared ductwork from Unit 3. 4 reactor buildings were damaged, 3 cores melted, and the valve in Unit 1 remains the clearest single-point inflection where things could have gone differently. Go ahead, pick one. Imagine you're an operator in Unit 1's control room on the evening of March 11th. You've got partial DC power back. Option A, you open the isolation condenser valves and hope the system works in the dark, trusting that cooling will resume even though you can't see water levels or temperatures clearly. Option B, you leave the valves closed to avoid potential leaks or uncontrolled cooling, waiting for more information and backup systems to come online. If you chose option A and it works, you might prevent the meltdown. But if you chose option A and the system has an undetected breach, you could flood the containment with radioactive steam and lose containment integrity even faster. If you chose option B, you're being cautious, following failsafe logic, and you might buy time for other rescue efforts. Or you might just guarantee that the core melts because cooling stopped and there's no plan B coming in time. The operators in Unit 1 effectively chose option B. Whether by misreading instruments, by procedure, or by fear of making things worse in the blackout chaos, MO3A stayed closed. The core heated, the fuel melted. Hydrogen built up and exploded. GG, you're looking at a meltdown. Alright, let's try another one. You're a regulator reviewing Fukushima's design before 2011. Option A, you accept the isolation condenser fail-closed logic because it prevents leaks during earthquakes, prioritizing containment integrity over cooling flexibility. Option B, you demand fail-open valves or a manual mechanical override so operators can always restore cooling even without power, prioritizing decay, heat removal over leak risk. If you chose option A, you get credit for guarding against loss of coolant accidents from broken pipes. But you set up a single point of failure where losing DC power means losing your last passive cooling shot. If you chose option B, you might introduce new leak risks, but you give operators a fighting chance to cool the core no matter what. Japan's regulators and TEPCO chose option A decades earlier. When the tsunami erased electrical power, that choice came due. Now, let's talk money. Yeah, baby. The title promised $200 billion, and that's far from a random figure. It's the mid-range consensus from multiple sources tracking Fukushima's long-term costs as of 2025. Decommissioning alone, the process of removing melted fuel, dismantling reactors, and making the site safe was initially estimated at a few billion. By 2025, Japan has spent or budgeted 5.2 trillion yen, about $35 billion, just on decommissioning, with projections running to 8 or even 51 trillion yen total, depending on how long fuel removal takes and what technology is required. Compensation to evacuees, businesses, and affected communities hit 9.7 trillion yen by 2021, roughly 65 billion. Decontamination of 1,800 square kilometers of farmland, forests, and towns, ongoing since 2011, adds another 5 to 6 trillion yen, call it $35 to $40 billion. Interim waste storage, the concrete and steel needed to hold radioactive soil and debris, adds 1 to 2 trillion yen. Added up, $35 billion decommissioning so far, $65 billion compensation, $35 to $40 billion decontamination, $10 billion waste, and you land in the neighborhood of $150 billion to $200 billion as a conservative baseline, but there's so much more. Broader economic impacts push the total higher. Japan shut down all 54 of its nuclear reactors after Fukushima, replacing that baseload power with imported fossil fuels. Over the decade following the disaster, that added roughly $100 billion in extra energy costs and lost export revenue. Tourism around Fukushima and the Tohoku region collapsed, costing tens of billions more. Fisheries, especially around Fukushima, remain controversial due to tritium water releases that started in 2023, even though the water is diluted to international safety standards. Some estimates factor in lost fishing income, ecological damage, and the psychological toll of evacuation, pushing the grand total toward $500 billion to $700 billion over 40 years. The $200 billion figure sits in the middle, covering the direct, measurable costs that are locked in, done deals, money already spent, or firmly budgeted. It's the number that's hardest to dispute, the floor, not the ceiling. Here's where it gets human. On March 12th, as Unit 1's pressure spiked and hydrogen built up, plant manager Masao Yoshida faced a choice. TEPCO executives in Tokyo ordered him to stop injecting seawater into the reactors, worried that the salt would corrode equipment and make the plant harder to restart. Yoshida, standing at ground zero with radiation alarms screaming, ignored the order. He kept the seawater flowing. That act of defiance almost certainly prevented even worse meltdowns in Units 2 and 3. Yoshida died in 2013 from esophageal cancer, which he said wasn't caused by radiation exposure, though he spent weeks in the plant during the crisis. Whether the cancer was related or not, the man became a symbol of the workers who stayed when every instinct said run. They called themselves the Fukushima 50, though the actual number fluctuated between 50 and several hundred depending on the day. These operators, firefighters, and engineers worked in rotating shifts, some facing radiation doses up to 30 rem per hour, levels that guarantee long-term health risks and can cause acute symptoms within hours. They jury-rigged fire trucks to pump seawater when all the normal cooling pumps were dead. They vented radioactive gas to prevent containment ruptures, knowing every release pushed them closer to evacuation limits. They sprayed the spent fuel pools from helicopters and ground cannons when it looked like the pools might boil dry and ignite, releasing even more radioactive material. By December 2011, a cold shutdown was declared. The reactors were stable, though the term stable is doing a lot of heavy lifting when 3 cores are melted and sitting in containment vessel basement. Let's be clear about what actually melted. In a boiling water reactor, fuel rods are bundles of uranium pellets inside zirconium tubes stacked like tall, slim soda cans. When cooling stops and temperatures climb past 1200 degrees Celsius, the zirconium starts reacting with steam, producing hydrogen and weakening the cladding. Above 2800 degrees, the uranium itself melts. In units 1, 2, and 3, the molten fuel, called corium, burned through the fuel assemblies and pooled at the bottom of the reactor pressure vessel. In some cases, it melted through the pressure vessel steel and dripped into the concrete-lined containment below, where it solidified into formations that look like frozen lava. As of 2025, only a tiny fraction of that debris has been removed. Robots sent in to survey and sample the corium keep breaking down due to radiation and heat. The current plan is to chip away at it piece by piece over 30 to 40 years. That's why the decommissioning bill keeps rising. They're inventing the technology as they go. If you enjoyed this video and want to see more like it, click the video on screen.